good. How are you?
I'm good, exactly. None is there.
I don't know.
Hi.
Hi there. How are you?
You're very good, yeah. So we have a problem with that. 601, they don't offer this semester, right?
Which one's 601?
That's a quantum lab.
Yeah.
So
Not
you,
this semester, but next semester?
no, so probably not this year.
Okay.
Probably that course will offer only in the fall.
Oh yeah, but this semester it was in the catalog, right?
Yeah, it is on
but
the
it was in
catalog.
the yellow highlighted. It's not being offered. So you are thinking about taking that one. Now you have to think about.
I'll find something else.
Yeah. So for you guys, I was thinking actually. I talked to Dr. Jayanti.
Yeah.
Maybe some course in chemistry.
Chemistry.
Chemistry they offer some this DFT kind of classes. There are two professors, Lee Thompson
Yeah.
and Pavel Kostelski. So these two guys are teaching. Maybe that might be in useful course for theorists.
Okay.
Yeah, think about that. Yeah. So you usually share the lecture,
Yeah.
these
yeah.
videos, right?
Yeah.
And everybody here.
Yeah. You have access to the channel?
Yeah. You sent me the email, I think, the first.
Yeah.
Thank you.
They're all there on the playlist.
Yeah.
Almost all of them. The three ones that were not in person are not yet. I go back and forth on this.
Yeah.
But like, what I want you to do.
Okay.
I'm sorry.
After 4 p.m.
I'm not so sure again.
You're not sure again. Okay. No worry.
I'm very bad at this.
No problem.
It's like, I love it, I hate it, I love it, I hate it.
Yeah. Okay.
I think before the end of the year.
Yeah. Okay. Did you try start makeup work?
I haven't finished much of it yet.
Yeah.
I have a makeup lab right after stat mech. So, yeah, we can work on it.
Hello, Ansari. Namaste.
Namaste.
How are you, Ansari? Good. How much you left?
Good.
That's good. Okay.
Let's get started. So last time we talked about two parameters, right? Typically, there are two length scales in superconductors. One is the coherence length, other one is the penetration length, right? These are the two things. So if you have a superconductor, this coherent length, usually it doesn't start right at the surface, right? It has to go into the superconductor. This is more like, you can think about number of this the Cooper pair concentration, right? So that's what, so here you don't have any, so then you have supercurrent, the carriers, they are developing into the superconductor. Then it's pretty much constant throughout the superconductor.
Does it say constant forever, or is it?
No, when you have the other end, so you will have another
Okay.
decay here, right? But throughout the superconductor is pretty much constant.
Okay.
So if you look at if you have a magnetic field, then we know magnetic field is going to decay into it doesn't decay immediately here, right? It has some penetration depth. So there's a comparison between this theta and lambda. So that's the important thing, right? That kind of separates this type 1 and type 2 superconductor. So here, so we have coherence length, then we have lambda L, right? These are the two things. So typically we define some quantity called kappa. So this is basically the ratio between this theta and lambda L. So if this kappa is greater than 1 over square root of 2, typically this is the situation for type 1. Everybody remember type 1 superconductors? They were the standard, this like all the aluminum, tin, niobium, these kind of things, right? So this means case greater than 1 over square root of 2 means this is greater than 1 over square root of 2. That means your theta is greater than lambda L over square root of 2. So I can just probably do it. I can't remember. Yeah, so this is fine. Yeah, theta is greater than. I think this is not 1 over just square root of 2. So that means theta is greater than square root of 2 times L. So that means theta is greater than lambda, right? That's basically what that means. Theta is greater than lambda means lambda is basically this length scale, right? So theta is this length scale. So this is larger than this one. So in the type 2 superconductors, this kappa is less than square root of 2. That means your theta over lambda C, lambda L is less than square root of 2. That means theta is less than square root of 2 times is coherence length. So that means in this case, sigma is smaller. So then that means what? So sigma, lambda is now longer, right? So this is, this defines lambda. Theta means this length scale, right? So that is, in this case, lambda is larger than theta. That's the case for the type 2. These are the high TC superconductors, right? YB0 and things like that. So ideally, if you look at, yeah, this is a situation, we already talked about this one, right? This is the most important thing. If you look at your, say, this is how the magnetic field decays, right? So that means you can think about what is the energy related to this, magnetic penetration. So actually, this is an energy penalty because ideally, if you have a superconductor, if you have a magnetic field, it should ideally go through it, right? That's what we expect. But if you have a superconductor, it cannot go through, right? So it has to be excluded. It should go around. So that means you need some energy, like we can say it's like energy penalty to exclude that magnetic field. So that means for this is the magnetic field, right? So then we have related energy. So look at this curve. So that is what related to no, this one. So because this is a longer one, right? That's related to this one. Can you see this blue one? This theta is much larger, right? That's what we have here. Energy related to this one. This is the free energy. So this is the how the magnetic field decays, right? So then the energy, the magnetic energy related to this one should be in the shorter length scale, right? So that is this one. So if you look at this energy penalty, we know superconductor and the normal, the free energy, Helmholtz free energy difference is simply this mu0 half mu0 hc squared over 2, right? So actually this energy is the energy penalty to exclude the magnetic field. So in this case, this energy is, we can say it is the energy to exclude the magnetic field, because you need to have some energy loss, right? To, if you have, because ideally it wants to penetrate the superconductor, but there should be something that doesn't let it do it, right? So that's what we call the energy penalty. Then, so this one, that is basically what it makes the superconductor, right? So this the coherence length means that's what defines the superconductivity. Whether you have these Cooper pairs inside the superconductor, that means you gain some energy to be in that superconducting state. So that's what this energy is. This is superconducting energy. That's what makes that material from normal state. So it has to gain some energy to be in the superconducting state. There are two energies competing here. One is to exclude the magnetic field. Other one is to be in the superconducting state. So you can see, for depending on whether type 1 or type 2, if it is type 1, we know theta is larger. This is larger, right? So that means this energy is large. If it is type 2, then this lambda is larger. That means this energy is larger. So you can see the difference. So if you look at this one, so you can see how that one. So this is the type 1 superconductor. You can see in this one, your theta is larger, this is larger, this is smaller. Now if you take this is more like positive energy and negative energy, right? Now if you take the total energy, how does it look like? From here to here, they all are zero, right? You have positive, negative, they cancel out, zero. Here also pretty much zero, but here you can see you have much positive, smaller negative, right? That means your total should be something like this. If you add these two, this is how it should look like, right? Can you see? That means what you have is a total energy penalty here, because that energy is higher. So net energy is now like penalty. Actually that's the interfacial energy. But if you have other way around, if you have a type 2 superconductor, in that case we know type 2 superconductor theta is smaller, the lambda is much larger. So that means if you look at, this is the energy related to this to be in superconductor, that's theta 1. So this is the magnetic energy, right, corresponding to this red curve, this one. So now if you take the total, what happens? These two are zeros, but here this value is much larger, right? That means if you take the sum of these two, you have this kind of total energy. So this means it has higher gain. So gain to be in the superconductor. So you can net energy is a gain in this case. For type 2 superconductor, you have higher gain at the surface energy. So in the type 1 superconductor, that's more like higher penalty to be for the magnetic field to be excluded. So here's the summary of that. Type 1, type 2. If you consider this for the type 1, you have more magnetic loss energy. Typically, these have much higher theta values, right? Like I said, type 1, your theta is much larger compared to lambda. So, but only thing is your TC values are small, right? They are standard superconductors. Even HC, that, well, they have only one HC, right? If you plot H and T and H, you have HC and TC. There's only one, right? So that values are typically very small in Teslas. But if you go to the type 2 superconductors, these theta values are small, but lambdas are much larger, right? Penetration depth is, because to type 2 superconductors you can penetrate much Also, we know they have vortices, right? There are some regions you don't have superconducting regions. So, but typically lambdas are larger. Then the TC also can be much higher, right? Like YBCO kind of materials. Also HC, we know in this one we have two, H and HT, we have TC. So this is superconducting, this is normal, right? But if you have a type 2 superconductors, we have second HC, right? HC1 and HC2. So this is a mixed state, right? Here it is normal. So typically HC2 can be much higher at Teslas, right? Okay, so that's pretty much about this correlation of coherent length versus penetration depth. Also we talk about type 2 superconductor, that means lambda is much larger than theta. We talked about vortices, right? Vortices means there are regions in the superconductor they are not superconducting. That means if I have a magnetic field, they will pass through here. Others, they cannot, they have to go around. But here, these regions, you will have, that's what they show if you use some magnetic probe here. So you will see only the places where you can see the magnetic. This same thing can be seen in superfluidity also. If you take a superfluid, you have vortices. So if you take a typically liquid, you have seen how this vortices happen, right? In this, if you have very strong water flow, so you see some kind of vortices, right? So exactly same thing happens here. So superfluids also have this kind of vortices, but they are mostly not the magnetic field, how the velocity changes, right? So in this part you have high velocity, here you have lower velocity, so the vortices. So you have seen vortices even in like this, the hurricanes and all these things, right? So in water especially you can see that. So these vortices are common for, like I said, superconductivity and superfluidity are very much analogous, right? So only thing is in superconductors you have Cooper pairs with opposite spins. So then if you have superfluidity in helium-3, we have two helium-3 atoms, right? So they all condense into lowest ground state. But helium-4 is different. Helium-4 is just one atom, right? They are bosons, right? So remember, they all are bosons, right? Even each Cooper pair is a fermion, but if you have a composite, they become like a boson, right? So here also each helium atom is a fermion, but when you have two together, you have already boson. But helium-4 atom, that's already boson. That's why you don't need another atom to have. So helium-4 is already in the boson state. Bosons can be at many bosons can be at a given state, right? There's no Pauli exclusion principle. But the fermions, you cannot do that. Okay, so then the last thing I want to talk about is this flux quantization. Same with three things we talked about. Superconductors, one is your resistance should be perfectly zero. Then we talk about it should be a perfect diamagnet, right? Kappa should be -1. So last thing is the flux quantization. This means if you have some ring, suppose superconducting ring here, if you have some external magnetic field, if you look at your magnetic flux through this ring, suppose typically flux, magnetic flux we write as B dot dA, right? That is your thing. So if you measure this flux, this one, they found this is always some quantized value. It can be 1 times some pi 0, 2 times pi 0, some constant value. So that's always quantized. So you cannot have any arbitrary numbers. So this pi 0 is a constant value. Actually that is very standard value given by h over 2e. So you can see here. Yeah. Forget about this e. This is some old unit. Typically, h over 2e. H is the Planck constant, right? Everybody remember. So E is the electronic charge. Here 2 comes because Cooper pair has 2 electrons, right? So that's what this one is. Pi, the flux through this ring. So when this happens, actually, everybody knows if you have a current in a ring, so then you have magnetic field using your right hand rule, right? So it's more like a solenoid. So typically, in this case, if I have current going like this, you have magnetic flux like this, right? Right hand rule. So this is what is this current actually. That's a supercurrent, right? So this is very important in superconductors. We call this a persistent current, because if you have a ring like this, if I connect this one to some maybe power supply and apply a current, so that current will never decay, right? Because it can go on forever, because there's no loss of current. So that's called the persistent current. So this is a supercurrent in a superconductor, if it is in a superconducting state. That's a nice thing about. So if you can introduce some current, and if it is superconducting, it will go forever. So this is persistent current. Okay, so now let's prove this equation. So I think it's an interesting thing to show. So this flux is this n times pi 0. Actually, experimentally people observed this one. You can see this is some like 1961 physical review letters. This group, Fairbank. So they measured this flux as a function of magnetic field. So they calculated the flux in terms of that h over 2e. Then they saw for every magnetic field, so these are the data points for different materials. So they found it's all come in this 1. So then if you go to higher magnetic field, you find it's exactly 2. So then higher magnetic field it is 3. So there's nothing in between, right? So this is very first experimental evidence. So that means your flux is basically, that total flux is some n times this h over 2e, this is a constant. So this n can be 1, 2, 3 like that. You can see exactly this. This is in terms of h over 2e. You have 1, 2, 3 like that. So they have shown even for higher. So how do you show this one? Let me show this one. You can easily prove it. This is a very good example how to do this one. Let's see how we can do this. You all can help me to do that derivation. Very interesting. So we have to calculate, first we'll calculate the current density J. Right? So what is J? E N V, right? So then we can write as momentum over mass. Right? What is MP? You can actually, that is standard value, but if you have electron in a magnetic field, you have this vector potential coming, right? So that means what you have here is really P minus Q times A, right? That is the vector potential divided by M. So is that clear? So everybody should know, if you have a scalar potential, you have electric field, we know how to connect the scalar potential to electric field. So same way we have magnetic field. Typically we due to magnetic field we have something coming like this dA over dt, right? So then the A is connected to magnetic field by this equation. I think you all know what is that thing. This is called the vector potential. Here this is scalar potential, right? So we know how they are connected to each other. So now also we know P. P is given by in quantum mechanically what? Minus right? So that I can write this one as minus IH cross grad minus QA divided by N. Okay. Is that okay? So now in this superconducting situation, so we have a ring, right? So I won't calculate this current J, supercurrent. Ideally that current, if you look at in the very deep in the superconductor, that becomes zero, right? Because superconductors, so there's no real current, but they all happen at the surface. So, like I said, we can define our, remember we defined something called the order parameter. Superconductors have order parameter, right? So we define this order parameter, say psi, as square root of n times E some I theta, because psi is a complex number, right? Remember we wrote our the free energy F S minus Fn as this A alpha times this order parameter squared plus order parameter 4 and things like that. Then you have magnetic term and all, right? So that order parameter you can write as, this is a complex number, you can write as this one, right? It's a complex number. Then what is I star? E minus I theta, right? No, complex conjugate. This is a real number. Is that it? So that means n is basically psi times psi star, right? If you multiply these two. So that means I can replace this n. Here if I want to calculate j I can write as E. Actually I can write this one as Q. Q is really 2 times E, right? So just remember that's a Cooper pair, right? So I just write as Q. J equals Q times N I can write as psi and psi star, right? But psi and psi star, they are actually operators, right? So that means you have to write this one psi star, then we have V, it operates on V times psi. That's what you have to calculate. Is that clear? So the psi star psi means N, basically you write that one as N, but since these operators, it should operate on what? Is that clear? Okay, now let's calculate this one, pretty straightforward. So if you do this, just do carefully. If you write this one, so J equals what? I can write as Q times psi star, oh, I erase that one. Psi is square root of n e I theta, psi star is square root of n e minus I theta, right? So then Q psi star I write as this one, right? Square root of n e minus I theta. It's fine, right? Then I have V times psi I can write as square root of n e I theta. So then V I can write as this way. So this is basically, if I do this one, Q, this one doesn't matter, right? So it doesn't operate. I will just write this way, n e minus I theta. V I can write as minus I h cross grad minus QA, that is over n, right? So then that I wrote V, then I have square root of n times E I. Is this clear for everybody? Okay, so let's do this one slowly. So if you do what you get here, Q, this one square root of n, they are just constants, right? I can write Qn over m. Right, then I have E minus I theta. This one, how do you do? So I took this one out, then I have minus I h cross. This grad will operate on E I theta, right? So then what do you get? So that means you have to first differentiate with respect to theta, then I get E I theta, right? So then I have I coming out, right? So then I have that I differentiate with respect to theta, but that means with respect to x, right? So that means I can write as, say, grad theta. So grad theta means now d theta over dx, right? Yes, okay. So this becomes this basically d over d theta whatever times d theta over dx, right? Is that clear? So then I have that's fine. So that's actually this part. Then what I have is minus QA times EI theta. That's it. You can go ahead and do this. If you do this, what do I get? So you can see EI theta, this cancel, right? So then what I have is Qn over m. Then I have I squared minus 1 minus plus 1. Then I have h cross grad theta minus QA. That's it, right? That is my total G. You can do this one, right? So now, if I take deep in the, so that's what this one here. So if you take deep inside the superconductor, this, if you take this J dot dl, that becomes 0. So that means actually, if I take, that means actually if you make this one 0, so because if you do that integral is pretty much 0, then what you get is h cross grad theta equals q times a. So now just do this one, h cross grad theta dot dl. I do this line integral over along the superconductor. Then what I have here is q times a dot dl. Both sides I just took the line integral of this one. Okay, so now that's it. That's all we have. Now h cross. What is this one? That dot dl means what? D theta, right? Because d theta over dl times dl. This is basically d theta. What is this one? A dot dl. Anybody remember the Stokes theorem? Line integral you can convert into surface integral, right? So A dot dl becomes what? Surface integral. Anybody remember Stokes theorem? B dot ds. B dot area. So this is a line integral with respect to L. A that becomes B. And E and M, you do all this. What is this one? B dot ds. That's flux. So this is nothing but Q times your total flux. So now you can see H cross times, what is this one? D theta. D theta, if you integrate over one cycle, you get 2 pi, right? If you do 2 times, n times 2 pi. So what you get is n times 2 pi. Right? Is that great? This one is it. So now if you do this one, your pi is basically, you can see what is h cross times 2 pi? H, right? So h over q times n. So this is, q is basically 2e, right? 2e times. So see, this is how you prove your flux is basically h over 2e times n. That's what we have, right? You can see it's not very difficult, right? It's nice proof. You can just, is that clear for everybody? I have it here, so you can follow through. Yeah. I have ignored these things all. You can see A dot dl means B dot ds and here. So typically we call this value as a fluxoid. Okay. Let's see over this Q. Okay. So actually from this one that value is basically h over 2 is like this 2 times 10 to the power minus 15 Tesla times meter square. Okay, so I will stop there, the flux quantization. Next one is, actually that's the last one I want to talk about. Then we are going to finish the superconductivity today. So we are going to talk about something called Josephson junction. This is really interesting phenomena. So everybody remember simple tunneling, right? If you have some metal, say it has Fermi energy, right? EF. So if you have another metal, it has Fermi energy here. If you bring these up closer, but they are not really touching each other. There's a small insulation there. So that means classically nothing can happen, right? But quantum mechanically we know these electrons here, they have some wave function. Then this wave function can tunnel through the barrier, right? So basically then you have some, from this EF, if I apply some kind of voltage, you have this much energy, then this electron can move into this region. That's what happens in typical quantum tunneling. But here we are talking about 2 superconductors. I have one superconductor, so then I have a second superconductor, then we have this small insulation. So then what happens to this? Cooper pairs, right? So we have Cooper pairs in this one. So these Cooper pairs can actually tunnel. Tunnel means this Cooper pair, it has a order parameter, right? It's like a wave function. That wave function will overlap with the second superconductor. Same thing if you have this Cooper pair in this side, that has its own, say psi 1 is this Cooper pair, the order parameter here. This one has psi 2, so that one can overlap with this side. So that means basically that's a tunneling mechanism, right? So that means at a time this Cooper pair can be here and this Cooper pair can be here. So we can easily do that one by doing this. So this is my superconductor 1, this is my superconductor 2, this is the barrier. So the barrier has to be thin enough, right? Otherwise you cannot have this overlap, right? So now, actually later you will find, now I am going to apply some voltage. So you will later find even without voltage, you can have a current in this Josephson junction. That's really a remarkable thing, right? So if you have I versus V, typically if your V is 0, I is 0, right? Except like solar cells or something, right? In solar cells, even if you don't have any voltage, you have a current because of that photo current generation, right? But for the superconductors, you will find even V equals 0, this Josephson current will have some kind of current even at 0 voltage. We call this a super current for this Josephson junction. So what here I'm showing, if you apply voltage, what happens? When this is when V equals 0, that means when you don't have any connection, right? Let's do first general formalism, how we calculate the total current. So how do you do that? So I can write, everybody remember how to write the quantum mechanical wave function, right? Time dependent quantum mechanical wave function, basically IH cross dc over dt, right, equals your h psi whatever. So this has the your special dependence, right? So like that you can write the Schrodinger equation for this superconductor 1. How do you write that one? This as the, you can consider this one as the your Schrodinger wave function or order parameter. Order parameter is a complex function, right? So this is the equation. Then you have this, if I apply voltage V, just imagine this is the same superconductor. So then, so this V will be shared half and half, right, between the two. Then I can write as V over 2 times Q, that is, will give you the energy, right, times psi 1. Then you have overlap of the order parameter from the second one. That I can write as like coupling constant K times psi 2. Psi 2 is the order parameter of superconductor 2. Is that it? Now if I want to write this one, how do you write the Schrodinger equation? IH cross dt psi 2, this is the order parameter here. That will be negative Q over 2, because voltage negative now, right? Times psi 2, that is. Then you have overlap from this one, that is K times psi 1. That's all. These are the only two coupled equations. You can easily solve. Is that clear how we write these two? Now what are the psi 1 and psi 2? Psi 1 you can write as simply square root of n1 e I theta 1. Psi 2 you can write as square root of n2 e I t2, right? These are the order parameters. Now can you substitute here? How do you write this part? If you take the first derivative, what do you get? d psi 1 over dt means, first this is constant, then you have to differentiate this one, then you get ei theta 1, then I, right? So then theta 1 dot, right? Then plus, then you have ei theta 1, then you have to differentiate this one, then you get half 1 over square root of n1, then you have n1 dot, right? Because theta 1 and n1 both have time dependence. You know how to do this one, right? Same thing you can do for psi 2. If you do that one, just plug in here. You do this one, you get these equations. So just same thing. You can see, yeah, that comes in the square 1 over this one, right? Right. Oh, here. This 1 over comes here. 2 also here. Click. Then just write psi 1 like this. Same thing you write like this. Straightforward, right? So now you can, you have actually, you can separate real and imaginary parts here. So ei theta 1 you can write as cosine theta 1 plus I sine theta 1. This one also you can write. Then you have all real parts plus some imaginary part. This equals 0. So then this part should be 0, this part should be 0. You get two equations from first one. Second one also same thing, right? You can write this one as cosine theta, sine theta, then you can separate real and imaginary. This equals 0, then this part should be 0, this part should be 0. You get two more equations. Is that clear? Pretty straightforward, right? So if you do that one, what you are getting is this. You get one equation, this dn1 dot, right? So that is dn1 d theta. You get this function. Actually, this delta is theta 1 minus theta 2. Please do this one if you have time. Then you get second one for the n2 dot here. So that one you get here. You have four equations, right? Then you get one for theta 1 dot. Here you have theta 1 dot also, right? So theta. Yeah, theta 1 dot also here. So that is d theta 1 over dt. Then you also have d theta t2 over dt, right? You have four equations, right? Two from first one. So then if you take the difference between these two, that is theta 1 minus theta 2, then you get this equation. Really? It's nothing, it's very simple. Is that clear? So the two equations, if you substitute this one, you get four equations. 1, 2, actually this is 2 because theta 1 dot, theta 2 dot, if you subtract 2 you get, that's it. So if you have this one, so now you can calculate the total current. So what is the total current? Current is basically, if you remember, current is related to N1 and N2, right? So, sorry, N1 plus Dn1 T2, because J is typically E and V, so that means it's proportional to your the N1 and N2, right? So that means if you add these two, you get your J value comes something like this. So that actually this is a constant, we call this a J0. Then if your J is given by J0 sine delta. So delta is basically is theta 1 minus theta 2. So then also we showed this this important thing. So d delta over this one, but here this, just imagine both N1 and N2, they are the same superconductors. That means N1 and N2 are equal, right? So that means this one and this one cancel, you get the, otherwise if you have two different superconductors, this still there, right? But for simplicity we assume both are same superconductor A and B. So then this part is 0, then what you have is d delta over dt is simply qv over h cross. That means delta is, if you differentiate, you get qv over h cross times t plus some constant, right? If you integrate this one, so this becomes t. So that means you can write actually that your this one, wrote this. So yeah, actually it's a d theta, right? If you want to write this way, ideally. But if v is constant, this is qv over. So important thing is this, your current is, you can write as this is the current, right? So this is the important thing. So your current is given by, so is it clear? This J came from directly from that N1 plus N2. So then you get this one, then let me write here. So this is very important thing. So little bit confusing, but you have to really understand this. So your J is given by some constant times sine delta. So delta is given by that delta 0 plus, if you have you can say simply QV over, if it's a constant V, QV over H cross. So that means I can write my J as J0 sine delta is delta 0 plus QV over H cross times T, right? So just imagine this is a constant value. If V is constant, this is V times T. This is, please listen very carefully, this is really important thing. Now, here, just imagine if your V is 0. That means is this clear for everyone? So, just only look at these three equations. So, this is my current. Now this delta is this one. Just imagine my V is 0. That means I am not applying any external bias, right? If V is 0, this is delta 0. That means I have, when V equals 0, my J, we call, right, J0 sine delta 0. That's a constant value, right? So this is some constant number. So we call this is DC current, because I didn't apply any voltage, 0 volt. Now if I apply voltage, what happens? Now V is here, now my current is QVT over H cross. Now what is my DC voltage? So, sorry, DC current. So if I, here when there's no voltage, now if I apply some DC voltage, so then we have this term, you can see this is a sine function oscillate with T. Then what is the average value? 0. Right? If you have a sine function, what is the average value? 0, right? That means if you apply voltage, your current is going to be 0. So that's so this is what I want to explain to you. If I have superconductor with the Josephson junction, if I measure current and voltage for this one, you get current at V equals 0. This value is basically J0 sine delta 0, right? From both sides. When you have a voltage, what is the current? 0. There's no current here. Because it oscillates, right? Oscillates with, I'm talking about the DC current here. DC current. So then, if you go above some critical voltage, then it becomes non-superconducting, right? If it's a non-superconducting, it will be more like some, typically straight. That's how, for metals, right? Linear IV. Then you have this one also coming here. This is how your current will look like. Sorry. So this becomes this one, then it is 0, then all of a sudden you see that is the Josephson current, the current. So it's very unintuitive, right? So if you have a real metal, how does the IV looks like? Linear, right? So that happens if you have this VC or this is critical current. above critical current it becomes non-normal metal, then it has this one, but if it is below TC, that means superconductor state, this current is actually zero. Only you have current at zero. That's how the Josephson current looks like. Zero, you have a current, then no current until you reach this one. But if you look at the AC current, that we know current oscillates. Oscillates with what kind of frequency? Your frequency is given by QB over so omega t, right? So that means your AC current will oscillate with frequency of QB over H plus. This is also very important. You can tune your frequency based on your voltage. This is little bit not easy to understand, right? Without applying voltage, you get a current. By applying voltage, you don't have current, but you have oscillating AC. This is called the DC Josephson effect. DC Josephson effect. So this is basically, if you have this oscillation, that is AC Josephson. Then you can apply this B also, some kind of sinusoidal wave. Then you can have different phenomena. This is, I think everybody should understand this one. So here, this is the important thing. For V equals 0, your DC current is given by this one. If you apply any voltage, your DC current is 0. That's what that one is. But AC current you can have it, right? So because that average value doesn't go to 0. So this one can be in the AC. So then if you want more, instead of applying DC voltage, you can apply some AC voltage. Then you can have even more pronounced oscillations in the Josephson current. That's AC. Okay, so then last thing I want to talk about, the SQUID, the superconducting quantum interference device. So this is probably the most sensitive device you can ever make. So this is so sensitive to really small magnetic fields. So in this one, what you do is basically you have one Josephson junction here. That means you have this superconductor. You have this one superconductor like this, say superconductor A. Then I have some insulator here. So then I have the second superconductor like this. So this is superconductor 1, this is superconductor 2. Then you have 2. So typically they make it something like this actually. It's easy to fabricate something in this circular pattern. So then what do you have here? You have one Josephson junction. You have another Josephson junction. If I can apply some voltage across this one, they are in parallel, right? So basically these are two Josephson junctions in parallel. But to really make use of this one, you have to apply some magnetic field perpendicular to this SQUID. That's pretty straightforward, right? So then you can write your the phase difference, because the current actually goes this way and through this one it goes this way, right? So then your magnetic flux will be different, right? In one way it is going, say, positive, in other direction it will be negative. If I apply some magnetic field, your flux will be positive and negative. Half, if I apply plus 5. In one, you have like pi over 2. In other one is more like minus pi over 2. Then the difference is pi, right? So then you can easily write for each one. So if you take this two paths, right? So you have JA, that means your current through first Josephson junction, this one you can write, just like we did previous one, you can write what is the JB across this one. So if you do that, you can show your JA is given by that same equation. So you have this delta sine delta, say in this one I say for the first one delta A, but now I get some additional phase because of the magnetic field. So magnetic field is B, then you have a flux given by B dot ds, right? Or this is same as A dot dl. So that's what this is. For the first one I have delta A, then you have flux going from P to Q, that is this one. Same thing, current coming here, P to Q going this way. The other one, same, P to Q is going in this direction. So then you can see in the line integral going this way and this way, right? It's opposite. So if you write that one, you can see this is one, this is actually this is more like minus pi by over 2, this is pi plus by 2. Now if you want to calculate the total J, if you add these two, you get J0. So now you have the sine A, yeah, so you have sine, two sine functions, right? Sine A plus sine B. So sine A plus sine B means sine A plus B over 2, then cosine A minus B over 2, right? So if you do that one, you can see, if you add these two, you can see these two cancel, you get only this one. If you subtract these two, actually delta A and delta B, actually that is delta A or delta B, actually that flux quantum. So we showed that one, right? So that delta T times delta L, right? So we showed that one. From there you showed delta T is basically some this flux, the fluxoid value, right? Pi over this value. So if you do that one, you can see these two cancel. If you add these two cancel, you get delta A plus delta B. So that is nothing but that this pi over that H over 2E flux. Remember, your total flux is given by n times this pi 0. So this is pi 0 is basically H over 2E. That's the pi here. So you can see you get this equation. So what is this one? You can see this has this some constant sine value. This is the important thing. This function, cosine function, oscillates with the magnetic flux. Even if you have a really small magnetic field, you will see very strong oscillations. So that's what typically, yeah, this is what you have. So even if you have, you can see these are like only Gauss. Everybody knows Gauss is a really small magnetic field, right? So Tesla means 1 Tesla means 10,000 Gauss, right? So that means 1 Gauss means really small field. So here we are talking about even if you have like 1 or 2 Gauss, you can see all that cosine oscillations coming here. So 10,000 Gauss, right? So 1 Tesla. So that 1 Gauss means a really small field. You can easily detect these oscillations from those squid magnetometers. They are used in very sensitive instruments and even in medical field. Very expensive. So because you have to use some kind of lithography technique, right? You can see here. So how these are generated, the two tunnel junctions here. So really in the micrometer scale, right? So, okay, so I think I will stop here. So this is the end of superconductivity. Like I said, superconductivity is very different from typical things, right? So only thing is I don't have time to talk about the BCS theory. That's the microscopic theory. That's very complicated. So but I think this Landau-Ginzburg formalism is good enough for you to get some idea. Okay, so next two classes I'll be talking about the magnetism. That's also a very important area. So you don't get to learn much about magnetism in regular classes. So that's important. But we have only two classes, right? I will try to cover that one in the, because no class next Tuesday. So you have long Thanksgiving break. So then we'll meet Tuesday after the Thanksgiving. Then only two classes, right? So that's it. So you guys, if you haven't finished your homework, it's time to work on that. So my plan is to finalize the homework grading over the Thanksgiving break. Then after that, I will do the term paper, right? So please start working on that one. So I'm not going to, I think, do very any serious evaluation. I just want to see whether you learned anything in the class, right? So to use any concepts you learned in this class, that's all. So just read the literature and try to understand. If you have any question understanding your whatever you are trying to write, you can email me or come and see me. So, yeah.
I left that marker up there for you to use.
Oh no, I think these don't work on.
Oh no, that one works. That black one.
Oh, this one.
Yeah, those right beside the mic.
Yeah, that's good. Yeah. Okay, so I will see you in next week. Yeah, not next week, right? Anyway, you are out, right? Yeah. So you will be back when, like, after break, right?
Yeah. For
Yeah.
like
But you will submit paper. Yeah.
Yeah.
That's it. Yeah.
I might be late on my homework, like the.
That's fine.
last
Yeah,
one.
yeah. Just take your time. So there are people who haven't still submitted some old ones. Take your time and finish all the homework. That's all.
Yeah, I will keep working on this, even like that. at home.
Oh, sure. Yeah, yeah. If you have any questions, send me email or
Yeah.
anything. Yeah. Okay. Yes. Thank you. Yeah.
I told her that I will send it over.
Click on H. This is H, not H plus.
I told her that I will send this. Last week.
That's E H.
Yeah.
Oh, yeah. Is there anybody else who was thinking about? No, you're fine. Yeah. So that 601. So 601 class is not offered in this semester. So you have to think about something.
Optics, sir.
Yeah, actually, I was talking to Dr.
That is not offered in the history.
Yeah, I talked to Dr. Jayanti. She said maybe to both of you it will be useful to take that quantum computing class in chemistry. So chemistry has these two professors. One is Lee Thompson. So they both are doing DFT. And the other one is Powell University or something. He's a Polish guy. You can look at their courses. So definitely I think so that will be more useful. Initially she was thinking about the course offered by Badri in mechanical engineering, but that is more, it's nothing, he is doing mostly classical, MD and those things, yeah. But I think this is more quantum calculations, yeah, TFT and things like that. So I think just look at, I think, she said those two will be more suitable for you to, yeah. So Lee Thompson and Powell was